Generative models are a class of machine learning models that learn to generate new data samples from the same distribution as the training data. They model the underlying patterns and structures of data and can produce new content such as images, text, audio, or even structured data. Here are the main types of generative models. 1. Generative Adversarial Networks, GANs. Invented by Ian Goodfellow in 2014. Concept: GANs consist of two neural networks. Generator: G generates fake data that mimics the real data distribution. Discriminator: D tries to distinguish between real data from the training set and fake data from the generator. These two networks are trained simultaneously in a min-max game. The generator aims to fool the discriminator by producing realistic data. The discriminator aims to correctly classify real versus fake data. Applications: image generation, e.g., deepfake images, style transfer. Super-resolution, enhancing image resolution. Data augmentation for training other models. Video generation. Advantages: high quality, realistic outputs, especially for images. Flexible architecture adaptable to many domains. Disadvantages: difficult to train due to unstable convergence. Mode collapse. Generator produces limited variations. 2. Variational autoencoders, VAEs. Invented by Kingma and Welling in 2013. Concept: VAs are probabilistic models that encode data into a latent space and then decode it back to the original form. Unlike traditional autoencoders, VAs add a probabilistic twist by treating the encoding as a distribution rather than a fixed vector. Encoder maps input data to a latent distribution, usually Gaussian. Decoder samples from this distribution and reconstructs the data. The key is the variational inference technique, which approximates the data distribution by minimizing the Kullback-Leibler (KL) divergence between the true and the approximate distributions. Applications: image and video generation, anomaly detection, data compression, drug discovery, molecule generation. Advantages: more stable training compared to GANs. Provides meaningful latent space for interpolation and representation learning. Disadvantages: generated data is often blurry compared to GAN outputs. Assumes Gaussian latent space, limiting flexibility. 3. Autoregressive models. Concept: autoregressive models generate data one element at a time, with each step conditioned on the previous ones. They model the joint distribution of data as a product of conditional probabilities. For example, for a sequence x sadface x1, x2, xn, x equals x underscore 1, x underscore 2, x underscore n, x sadface x1, x2, xn, they model below values. Types of autoregressive models. PixelRNN/PixelCN for image generation, predicting pixel by pixel. WaveNet for audio generation, predicting sound waves sample by sample. Transformers, e.g., GPT for text generation, predicting words or tokens sequentially. Applications: natural language processing, e.g., GPT, BERT. Image generation, PixelCN. Audio synthesis, WaveNet. Advantages: high-quality outputs, especially in sequential tasks like text or audio. Easy to train compared to GANs and VAEs. Disadvantages: slow generation because each output depends on the previous one. Hard to parallelize during inference. 4. Normalizing flows. Concept: normalizing flows are based on transforming a simple probability distribution, like a Gaussian, into a complex one through a series of invertible and differentiable functions. The transformations are designed so that both the forward data generation and reverse data inference processes are tractable. The probability of the data can be computed exactly, which is a significant advantage over GANs and VAEs. Applications: density estimation, image generation, e.g., glow, anomaly detection. Advantages: exact likelihood computation. Invertible structure allows both data generation and data reconstruction. Disadvantages: computationally intensive due to invertibility constraints. Complex architectures required for high-dimensional data. 5. Diffusion models. Concept: diffusion models generate data by gradually adding noise to data and then learning to reverse this noising process to recover the original data. The idea is inspired by thermodynamics and the concept of diffusion in physical systems. The training process teaches the model how to denoise data step by step, and the generation process starts from random noise and progressively refines it into realistic samples. Popular models: DPM, denoising diffusion probabilistic models. Stable diffusion for high-quality image synthesis. Applications: image generation, e.g., DALL-E, stable diffusion. In painting, filling missing parts of images. Super resolution. Advantages: produces highly detailed, high-quality images. More stable training than GANs. Disadvantages: slow sampling due to multiple denoising steps. Computationally expensive. 6. Energy-based models, EBMs. Concept: EBMs assign an energy score to each data point, where lower energy corresponds to higher likelihood. Instead of directly modeling probabilities, EBMs define a scalar energy function, and the goal is to learn this function such that real data points have lower energy than fake ones. Applications: image generation, anomaly detection, reinforcement learning. Advantages: flexible modeling of complex distributions. Can combine with other models, e.g., GN-EBMS hybrids. Disadvantages: difficult to optimize. Sampling can be inefficient. Summary table. Generative adversarial networks, GANs. Key features: adversarial training, generator versus discriminator. Applications: image, video, and audio generation. Strengths: high-quality outputs. Weaknesses: training instability, mode collapse. Variational autoencoders, VAEs. Key features: probabilistic encoder-decoder architecture. Applications: anomaly detection, data compression. Strengths: stable training, interpretable latent space. Weaknesses: blurry outputs. Autoregressive models. Key features: sequential data generation, token by token. Applications: text, e.g., GPT, audio, e.g., WaveNet, images. Strengths: high quality, sequential generation. Weaknesses: slow generation, hard to parallelize. Normalizing flows. Key features: invertible transformations for exact likelihood. Applications: density estimation, anomaly detection. Strengths: exact likelihood computation. Weaknesses: computationally intensive. Diffusion models. Key features: gradual noise addition and removal. Applications: high-quality image synthesis, e.g., stable diffusion. Strengths: highly detailed outputs. Weaknesses: slow generation, computationally heavy. Energy-based models, EBMs. Key features: assigns energy scores to data points. Applications: image generation, reinforcement learning. Strengths: flexible modeling. Weaknesses: difficult optimization, slow sampling. Each type of generative model has its unique strengths and weaknesses, and the choice of model depends on the specific application and requirements, such as data type, quality expectations, and computational resources.